Hello students, welcome back to the next module. Students, in the last module we have derived expression for kinetic energy in SHM. In this module we will derive expression for potential energy. So let's start with expression for potential energy. So our straight line path LOR, and let's consider a particle of mass m performing SHM with an amplitude A. Students, let the particle be at point P at a distance x from the mean position. We know in SHM there is a restoring force acting on the particle continuously. So restoring force on the particle at this position will be given by the formula. Yes, it is F is equal to minus kx, where k is the force constant. Now students, let us displace the particle further by a small, infinitesimally small displacement dx against this restoring force. Like this, say the particle goes from P to Q through a small displacement dx against the restoring force. Since there is a displacement here, we know work is done. So the small work done during this displacement dx will be given by, so dw is equal to, students, we know in physics work done is the dot product of force and displacement. Therefore dw is F vector dot ds vector. Now by the formula for dot product, we know the next step will be dw, work done will be F dx cos theta, where theta is the angle between force and displacement. Now what is the angle between force and displacement dx? So let's have a look at this. As you can see in the diagram, restoring force is towards left, displacement dx is towards right. Therefore angle between them will be 180 degree or pi radian. And therefore the formula of work done dw will become F dx cos pi. We know cos pi is minus 1, therefore students, dw is equal to minus of F dx. Let us substitute this formula of dx, and therefore dw now is written as minus of F dx. Now students, let's substitute the value of force in the expression of work done, and therefore dw becomes minus, and in the brackets minus kx into dx. Minus of minus is plus, therefore dw finally becomes kx dx. Now students, if dw is small work done for a small displacement dx, therefore total work done to displace the particle from mean position to any distance x is given by, therefore work done will become integration of dw. dw stands for small work done. During this entire process, such small work done are done, and total work done will be integration of dw. As we know, dw is k dx. Let us substitute it here, and the value becomes integral k x dx with the limits x is equal to 0 to x. That is, particle moves from mean position to any distance x. For that duration, for that displacement, we are calculating the total work done. Students, we know k is constant, and therefore it becomes k is outside of the integral sign, and it becomes integral x dx from the limits 0 to x. As we know, integral x dx is x square by 2 plus c, so next step becomes w is equal to k x square by 2 from 0 to x. Students, here plus c will not come because we have limits of integration, and hence k x square by 2 with the limits 0 to x. Let's go for the next step, students. We know how to get rid of this limit sign. We have to first substitute the value of upper limit in the variable, which is fortunately x itself, and hence the next step becomes x square by 2 minus, and let's substitute the lower limit in the variable x now, and therefore this becomes x square by 2 minus 0, which will be nothing but k into x square by 2. Students, this can be rearranged and written as w is equal to half k x square. So this is the value of work done. Now as we know, work done is stored in the form of potential energy. Therefore potential energy also has the same formula, half k x square. As k is m omega square, potential energy can also be written as half m omega square x square. So these two expressions are the formula for potential energy. One more important thing, students, in the expression of potential energy, we can clearly see the presence of x, that is displacement. As particle vibrates, displacement changes continuously. Therefore, potential energy does not remain constant and changes continuously. Let's check the value of potential energy at first mean position. We know at mean position x is equal to 0. If I substitute the value of x in the formula potential energy, this becomes half m omega square into 0, which overall will become 0, and hence at mean position potential energy is minimum with the value 0. At extreme position, we know, students, x is plus and minus a, and therefore the formula potential energy becomes half m omega square into plus or minus a square, which is a square itself, and it takes the maximum value half m omega square a square, also written as half k a square. So at mean position potential energy is 0, at extreme position potential energy is maximum. Now let's summarize the discussion, students. So as we learned today, at any position x from the mean position, potential energy is half kx square or half m omega square x square. At mean position, potential energy is 0. At extreme position, it is maximum with the formula half k a square or half m omega square a square. As the particle goes from mean position to the right extreme, potential energy increases, and it goes from right extreme towards mean position, potential energy decreases, with the minimum value at mean and maximum value at the extreme positions. That's all in this module, students. See you in the next module.